I'm a data engineer at Simple. My Twitter name is @OceanKidBilly. And I'm going to talk about data engineering architecture. I'm going to focus on a little bit of Python, but a lot of sort of higher level work, sort of how we've structured our pipelines, how we've built data engineering, how we use the warehouse. And I'm going to talk a lot about mistakes we've made, things that we've learned because we did it wrong the first time. So I have a few examples of that. But what I really want to start with sort of a leading question is, why does Simple have a data team? Like, why is there a data engineering team at Simple? What is our goal within the company? Because if you look at engineering as a whole and like the functional teams, it's pretty clear what all these teams do, right? So back end actually builds core banking services, front end and mobile build clients. You know, if you go to simple.com and sign up for a bank account and you log onto your app, you know, you're interacting with clients from either front end or mobile. Infrastructure builds, you know, sort of core infrastructure, helps us ship code. Security does security things. It's always good for a bank to have a big security team. So where does data fit into all of these teams? Well, it turns out that the rest of the company needs to answer questions about how the business is doing with data. And everyone wants to know like facets of customer behavior, whether it's like marketing and product, trying to figure out how customers interact with the application. We have a huge customer service team. They need data to figure out if they're serving customers well. So the data team, we exist to help the company sort of make decisions and tell stories with our data. So how do we get this data? Simple started out with a service-oriented architecture. The company now runs on more than 35 separate services. And almost all of those each have their own Postgres database. So that's a lot of databases, right? It's a lot of places to get data from. So I'm sort of going to pose a question here. In a world without a data team or a data warehouse, what would it look like to answer what should be a pretty simple business question about our data? So we want to find all the users who have made a transaction greater than $1 in the past week. And in theory, this should be a pretty simple question for us to answer. But what does this look like without a data warehouse or a data team? So you've got scary production database number 1. And you've got scary production database number 2, and assuming that your ops and DBA folks will let you log in to your production databases, either that or they're going to have to download or like output this data to CSV for you. You pull it out as a CSV, you pull it into R Python, you do the join in memory, and then you go from there. That's kind of a pain. That makes a lot of assumptions about how you get at data. And if you start to answer questions that are more complex and you've got 35 different databases that you have to do this for, it gets tedious. This is how Simple used to work. In the early days, this is how like the young data team, which was 2 people, worked. They would do dumps from production and do their work in Python. So what does it look like when you have a data warehouse? Well, if all of those databases are in one warehouse, it's a pretty straightforward SQL statement. It's just a regular join. So the data warehouse lets us collapse 35 individual DBs, each for a separate service, into essentially one database. To the analyst, it just looks like a database. So we're the engineers, and the business through dashboards, you know, dashboards that work with SQL. There are a lot of dashboarding tools, so that they appreciate having all the data in one place, and we have controls over that in terms of permissions. The warehouse lets us get data to everyone from one place. So what does data engineering do? We build the tools and systems to make data available to everyone who needs it. So that is our job. And our data warehouse of choice is Redshift. So I'm going to talk a little bit about Redshift and what it is, sort of what we've learned while using it, and sort of some pointers for using Redshift if you choose it as your data warehouse of choice. So to start with, why would you want to use Redshift? Like, why use Redshift and not Hadoop or some other data store? One of the biggest ones, honestly, is that it's SQL, right? It was forked from Postgres at 8.2, so you know, it's more or less just SQL. If you know SQL, you can query Redshift. It's got incredibly fast load times from S3. So using S3 is like an intermediate stage to get data into Redshift, which is something we do a lot, is incredibly fast. It's got very fast query times. Redshift is really fast if you model your data correctly, which we'll get to in a minute. The security model is the same as the rest of AWS's security model, so you can leverage like IAM and roles and that sort of thing to give people permissions to get in. And one of the biggest things is that the rest of Simple all runs on EC2 and runs on AWS. So it's sort of a no-brainer for us, right? Like we already have services running in EC2, we already have data stored in S3. Redshift was a pretty clear choice as a warehouse for us. So here's a wall of text. And this is a wall of text written by the Amazon Redshift documentation writer talking about the database. And it's a little businessy, but I think there's actually some good things in here. And I'm going to walk through sort of these highlighted lines. So enterprise class, relational database query and management system, massively parallel processing, columnar data storage, targeted data compression. So this reads like sort of a business line, but these things are actually really important to how you use the warehouse. So let's talk about enterprise class relational database query and management system. It quacks like a SQL database, right? It looks like any other SQL database. Like I said, it was forked from Postgres 8.2. There are some functions that aren't available that are in Postgres, but for the most part, it complies with the SQL standard. The JDBC and ODBC connectors that you already have work out of the box for the most part, which is really nice. So a lot of my work in Redshift happens via CycloPG2, right? The Python connector. It just works with Redshift. It's totally fine. The query language, like I said, it looks a little different, but it's pretty close. So massively parallel processing. What does that mean? So if you stand up a Postgres instance, you've got like one node database, right? You have a Postgres instance. You have like an EC2 box or RDS. It's one instance of Postgres. Redshift is parallel. So it splits your data amongst many compute nodes. So you distribute your data across a bunch of nodes. And within those nodes, they're split among what they call slices, which is allocated at like a portion of the node's memory and disk space. So Redshift can parallelize both data storage and data queries. And part of that parallelization is with these things called dist keys and sort keys. So Redshift not only allows you, but forces you to decide and think about how your data is both distributed and sorted. And this can make a huge difference in your query times and how effective Redshift is to you as a database. So I'm going to take a look at this create statement. So this looks a lot like a normal like Postgres create table statement. You'll notice that we have to specify an encoding, so a compression encoding at the end. And then in this case, we're going to distribute the data by user ID. You can assume it's a UUID. And we're going to sort the data by when recorded. So it's often really useful to have your data sorted by timestamp. So yeah, Redshift emphasizes the use of these two keys to specify both distribution and sortedness. And you can leave them out, but if you do leave them out, Redshift will make some assumptions for you, and those assumptions might result in your queries being quite slow. So performance could suffer if you don't think about them. So let's look at an example. So in that create table example, what we did was we distributed the data by user ID. So user ID 1, all pieces of data that come in with user ID 1 are going to compute node 1, and all pieces of data that come in with user ID 2 are going to compute node 2. Same for 3, because Redshift is doing like hash space partitioning on user ID to go to the different nodes. But this is actually something that we saw in production. We were like, all right, well, we're using UUIDs. It should be very evenly distributed. But we noticed that one node was just like growing and growing. And we were getting really close to the limit of disk on that box. And we're like, what is happening? So this is what was happening. We had a lot of messages come through with user ID equals null. And these weren't invalid data. Like this was actually valid data, just sometimes for this particular use case, there is no user ID attached. So we had to recreate the table and redistribute the data. So this is the new table where we said, all right, the disk key is even. So basically we're going to distribute the data evenly across all nodes, which fixes our problem with disk space, but actually started to make some queries slower. And this is like, this is how it looks now. This is a trade-off that we had to make. Because now, before, if all the user IDs for a given user ID lived on a single node, when you needed to join two tables together, that join could happen on that node, just on that node. Now that we've distributed user IDs across the whole cluster, those joins require shuffles across all nodes. So we saw some queries get slower, and we fixed our disk problem, but our analysts also noticed that some queries were slowed down a little bit. So it requires trade-offs, and this is one that we saw in production. So here's another one that we saw. I'm going to talk about sort keys, so data sortedness. So in this case, I'm joining two tables based on user ID. Distribution aside, if your data is not sorted, if you don't have a sort key on this, what it's going to do is it's going to create a hash join. So this, if you've never used the explain query in Postgres to Redshift, it tells you exactly how it's going to execute your query, and is really useful in figuring out, all right, my query is slow. Why is my query slow? So in this case, we're joining the transactions table with the goals table. The goals table is going to be the smaller one, so we're going to build a hash table with the goals table, and then to join the two together, we're going to probe it, as we walk through the transactions table. And we learned that in Redshift, your hash table for a join can spill to disk. Not only can it spill to disk, it can fill up all the available disk space on your cluster, and it can cause the entire cluster to go down. We had this happen more than once before we fixed it. We still see it get close these days. Redshift has query timeouts, but they're not on by default. So if you're running a Redshift cluster, I highly recommend setting some sort of reasonable timeout for your query, else this happens. Because this is like a very real use case. You don't have to have that much data before you start building these giant hash tables for joins and start seeing them spill to disk, and suddenly you see your disk usage basically go to 100% on multiple nodes. So to move on with this example, here's an interesting fix. So Redshift lets you create temp tables, and it's actually really cheap and fast to create temp tables that have different data distributions and different data sort keys. So in this case, we're creating two temp tables, one with transactions, one with goals, both distributed by user ID and both sorted by user ID. So now when we do the join, the query plan actually does a merge join, which can basically be streamed in memory, and it's really fast. It's amazing. It's faster. It's been faster for us to create a temp table where we get merge join behavior than to just like do a hash join. Like even if it's not spilling the disk, merge joins in Redshift are so fast. So this is an example of where like thinking about sort keys is really important in your queries. So back to the business speak, columnar data storage. So I think this was touched on a little bit in the Feather talk earlier. If you have a columnar database and you're querying columnar databases, you really want to try to avoid all select star from queries. You always want to limit only the columns that you're actually working with. And the reason for that is the way that Postgres stores data is it stores it row-wise, right? So if you select A and B from the table, and it's just like select A, B, all of A, B, you have to do a full table scan. So with Postgres, you're doing a full table scan, you're throwing away everything but A and B, but it's the only way to get at all of A and B. It has to scan all rows. Redshift doesn't store data in rows, it stores data in columns. So when you select A and B, all it has to do is fetch the columns A and B from disk. So the more select, in this case, like if you do a select star, unless you really need all of that data, you're throwing everything away in terms of I/O. So always try to limit how many columns you're selecting. So now we're going to talk about compression. So Redshift has very efficient targeted data compression encoding schemes. So Redshift, I think by default it won't encode your data, but you can select an encoding for your data to compress it. A really nice thing that Redshift will do, if you already have data in a table, you can run analyze compression, and Redshift will take some subset of that data and recommend a compression for you, which is really nice. Quick caveat, that SQL call, analyze compression, requires like a full table lock. So I would not recommend doing this for a table where you're actively loading data or serving queries, because it will lock that table until it is done. Compression is really important for Redshift, especially like keeping your disk sizes, like keeping your disk reasonable. It improves both query performance and storage overhead. So it improves query performance because if you're pulling like I/O, if you're pulling encoded data off disk, that's much faster than unencoded data. And then of course it improves your storage overhead, right? Because you're storing less data on disk. I gave a short lightning talk on columnar compression. If you're interested in how Redshift encodes data, there's a lot of information there. There are a lot of really clever tricks that Redshift uses for different types. So that's there on GitHub. So now sort of the grab bag of important operational notes, things we've learned while using Redshift. The first one being that Redshift is an ACID compliant database. It supports fully serializable isolation levels. And like, okay, well, what does that mean for me, like running Redshift? It means that transactions can be kind of expensive. And the commit queue for transactions can back up. So if you're thinking, oh, I'm gonna stream data into Redshift, I'm gonna load data into Redshift every minute, that probably won't work, because we tried it. We tried loading data like every 3 to 5 minutes, and we had to back it off to about 10, except for critical tables, because we found that that like with our query load and all these loads happening, our commit queue is backing up. So remember this when you're thinking about loading data to Redshift and trying to stream data in, if you're going to do that. Redshift has a maintenance window. Redshift has a maintenance window every week, probably like 2 a.m. Ours is 2 a.m. on Monday. If you're building systems that require uptime, systems that expect Redshift to be up, systems that have health checks and might page an engineer in the middle of the night if Redshift goes down, highly recommend building those systems to be resilient to this maintenance window. We still haven't, we got paged for this last week. Like we're still, every once in a while we still get paged for a maintenance window because there's some system that doesn't account for it properly. Redshift, so varchar is a common data type in SQL databases. Redshift lets you specify varchar max, which is basically varchar 65,535 bytes. And you think, why would I ever specify something that big? Well, the answer is because Postgres has a text type. And you can put about as much as data as you want in the Postgres text type. And a lot of people use it, and that translates most closely to this varchar max type. But it's really expensive. Some joins won't work. You'll get errors like error 8001 detail. The combined length of columns processed in the SQL statement exceeded the query processing limit of 6,535 characters. Stuff like that. So when you're thinking about varchar max, remember it can be pretty sensitive when doing joins. And then the last one is Redshift is a black box. So basically they ship software updates sort of like in the Google Chrome manner. They just, except they do even worse than that. They just ship them behind the scenes. Like you never know when Redshift is updating, it just updates, right? And they've broken the query planner on us only once, but it happened. We had a query that just stopped working because the query planner broke. And when Redshift goes down, so this is good and bad, right? When Redshift goes down, there's nothing you can do. You just have to wait for Amazon to fix it. So it's bad because Redshift is down. It's good because like you're not the one fighting the fire. So it's a pretty big trade-off. But like I have this on here, but honestly, Redshift has been incredibly stable for us. Like it has gone down. Oh man, very rarely. Like I can count on one hand the number of times we've seen it go down. And when I say go down, I mean for a period of 10 or 15 minutes. It's usually when some sort of node fails and they have to replace a node. So yeah, queries look like Postgres. Redshift is forked from Postgres, but it's not Postgres. And you need to remember that when thinking about like distributed nature. And it's distributed nature when like building tables and queries. So we're at Python conference. What are the ways that you can talk to Redshift with Python? There's sort of the venerable psycopg2 library. That library can kind of be a pain to install. If you've ever tried to install that library, especially if you've tried to install it with like SSL, it can be kind of painful. There's a brand new Python 3.5 plus pure Python Postgres library called async.pg that I haven't used yet, but it's supposed to be incredibly fast and looks quite good. And we might look at starting to switch some of our psychopg2 usage to that. And for our analysts who have had trouble installing psychopg2, we might start pointing them at async.pg. There's a SQL Alchemy dialect for Redshift that sort of builds on top of the existing SQL Alchemy stuff with some Redshift specific operators. And then finally, we at Simple, we have an open source library to interact with Redshift called Shift Manager. And it's like a bunch of helpers, like some for creating users, doing schema reflection, which helps with like deep copies of tables, deep duplication, migrations, and then poorly documented, but in there, there's some tools for doing bulk loads of data from Postgres to Redshift, and the same thing with bulk JSON. We probably need to write some docs, but they're in there if you go look at the code. So if you're working with Redshift, you might find some useful stuff in there. All right, so let's talk about Simple's pipelines. This is the entirety of Simple's data pipeline. So boxes with borders are our services, and then everything else is sort of connective tissue. So Kafka, RabbitMQ, message brokers, things holding state like S3, Redshift, Elasticsearch, and that sort of thing. So this is kind of an eye chart. So let's walk through what each of these things does for us. So we have a service called Sawtooth. It's old. It's basically Postgres replication in that we crawl Postgres on a schedule, like every 10 or 15 minutes, and then use Zookeeper to store the timestamps for the last crawl. And when we crawl it, we fetch like the last 15 minutes of data. We put that to RabbitMQ. That goes to Redshift. We have some really tricky bugs in this library around the updates of rows. We found that doing this can be a little tricky when you have a lot of row updates, and sometimes we have some tables with like poor data models where it's not clear when the row was updated. And so we found some subtle bugs in here, and we're moving away from this towards a more robust solution that we call PG Kafka. So in Postgres 9.4 plus, there's this new feature where you can basically, it's called logical replication slots. And what that does is you can have Postgres stream every change in the database to something. And for us, that's the Kafka like message queue, right? So it's more or less a real-time stream of the write-ahead log to Kafka. So every update, every insert, every delete, all of these come through to Kafka, and then downstream, talk a little bit about how they get into Redshift. Right now, I'm working on a question that I've gotten before is, okay, when engineers in the backend team make changes to the Postgres database, how do you know those changes are reflected in Redshift? And right now the answer is an analyst realizes that something is missing, comes and talks to us, and we have to backfill data. The answer in the future is going to be we can also replicate DDL statements like create table and alter table downstream and apply those to downstream databases. We're obviously not going to do this with destructive statements. I think automatically applying delete table and delete column statements would be very bad. So that's not going to happen. But anything additive, we're working on streaming those downstream. Here's the grab bag of things. Like I think any data engineering team, you eventually end up just like with this pile of things that have to handle different things for the business. So we've got a service that handles data transformation. We've got a service that handles emails. So anytime a customer like signs up and we need to send them lifecycle emails, we've got a service that does that. We're folding some of these things into one sort of big service called Estuary that is built on Kafka streams and will let us build like individual jobs and sort of have all this in one place. It's really tough to manage multiple services. Every one is sort of like is a weight on the team in terms of being on call and that sort of thing. And then finally, we've got a service that handles user events from clients. So every time like you interact with Simple on your phone or on the web, it sends events into this HTTP endpoint. Those go into Redshift. All right, so let's talk about, I've talked a lot about putting data onto message queues. How do we get that data from the message queues into Redshift? We have a service called Horizon that's like our ETL service. So we read from both Kafka and RabbitMQ. We batch those messages and put them to S3. And then we have a loader that loads those batches from S3 into Redshift. One kind of neat piece that we have is it'll take a batch. Redshift has this thing called a no-load copy, where you can attempt a copy against Redshift, and it'll tell you if it's pass-fail, like, hey, this copy that you're going to try to do works, or hey, this failed. If we have a batch that fails, we'll start bisecting that batch and extract the bad messages out and put them to S3 for something to happen in the future. Right now that something is they're just sitting there and like none of us actually wants to go deal with it. Like, you know, they're there for the future. And so that's basically it. We got a batcher, we got a loader. We've got like 6 or 7 instances of Horizon running at the same time, loading from S3 into Redshift. So we use Zookeeper to keep a table lock. So those instances talk to Zookeeper and say, hey, are you loading is the transaction table being loaded right now? Yeah, okay, I'm gonna move on, load a different table. So we use Zookeeper as like our locking mechanism, so all the instances of Horizon can load in parallel. One decision, this happened before I actually showed up, that was made sort of early on about the data schema that I thought was really smart is this is all that it takes to send data to Redshift. You need a table name and you need a datum with column like key value pairs. It's with the column name and then the value. And so if you want to put data in Redshift at simple, all you need to do is create the table. Horizon will pick up that table because Horizon queries Redshift like every 10 minutes for table schemas. So create the table in Redshift. After 10 minutes, Horizon will pick it up, put it in a schema registry, and then any data sent to Horizon, it'll automatically start loading that data into Redshift. So you don't have to do a bunch of fiddling between you and Redshift. You just say, all right, I'm going to create the table. I'm going to start sending the data to the queue that Horizon consumes from, and boom, we're done. Moving on to a couple of our other services, we also have a transaction search service. So if you sign up for a Simple account right now and you spend some money and you go to search your transactions and you see some analytics and that sort of thing, that's all served by a service from the data team. It's ingesting from Kafka, putting to Elasticsearch, and then it serves HTTP requests from clients and mobile. And then finally, our biggest Python service. At some point, somebody said, all we really need is like a janky version of cron. And at that point, Jankron was born. And what Jankron does is like purely run scheduled tasks. Basically, it's scheduled tasks to get data from third parties and put it into Redshift. So we pull data from like our email, our third-party email provider. We pull data from Nanigans. We actually pull a lot of GitHub data. So we run GitHub Enterprise, and every night we pull everything that happened in GitHub that day and put it into Redshift so that our our business folks can like sort of look, our engineering leadership can sort of look at how we're working on GitHub and that sort of thing. And that's actually been a pretty fun one. That's pretty fun data to analyze. So those are all the pipes. That's all of simple data engineering. So what have we learned from building all of this? The first one is that we're moving away. The whole company is moving from RabbitMQ to Kafka. RabbitMQ was in place like when Simple started. We're transitioning to Kafka. Why are we doing that? So one reason is Kafka has this idea of a retention period. So you can tell Kafka how long to hold on to your data. And at any time, let's say that your service fails, goes down for some period of time, Kafka stores the last offset that you stored from that data. And like you can go back in time at any point from Kafka, right? Like you can say, hey, I advanced all the way to offset 2 million, but I need to go back to like offset 1,500,000. Let's go back and replay all this data through the pipeline. And that's super valuable. Whereas with Rabbit, like if you hack a message, like you got that message, you better not drop it. The other thing is Kafka actually has like real network partition tolerance. We've had instances in the past where Rabbit, like, and to be fair to Rabbit, like Rabbit is very clear in the documentation up front, does not tolerate network partitions well, like first line in the documentation. What happens if two Rabbit nodes stop talking to one another, basically the one node that got separated is like, I'm in a bad state, you need to fix me. And by fix me, I mean you need to drain those messages manually to like your computer and then put them back through your pipeline by hand. And that didn't happen too often, but when it did, it was kind of a big deal and super painful. So the next one is metrics and health checks. I just talked about a bunch of services. There are a ton of moving parts to keep track of. If you don't have your services instrumented with metrics and health checks, deployment is scary. You don't know when your stuff is broken. It's really hard to know like the health of your systems without having these things in place. Flask and Django both have libraries that support metrics and health checks. And honestly, I'd never written any HTTP service with a metric or a health check before I got to Simple. But all of mine in the future will have them because I think they're really important to knowing like observability for your systems is really important. Like knowing the health of your systems is incredibly important. Postgres. It's a really good default. It's a great data store, whether you need like relational, JSON, key value. It's a great solution, but you should be flexible, right? So in the case of like doing transaction search, Elasticsearch, which is built on Lucene, has a lot more flexibility in terms of NLP. You can scale it better. The scaling story for Postgres with full text search wasn't quite clear, and the query capabilities were a bit more limited. So I always tell people like default to Postgres, but in certain specific use cases, you might need to look at other databases. I mentioned this earlier, the flexibility of our data model with Horizon has made scaling our Redshift schema a lot easier. And along with that, table migration tools for Redshift have made schema management easier. We use Flyaway, which is a Java library, but if you haven't used Alembic for Python, which is a table migration library, I think it's written by the same person who did SQL Alchemy. It's really good. If you're doing your migrations, database migrations by hand, you should take a look at it because it's just a really nice software practice to have. Celery, the task queue, the Python task queue. I love Celery. We used, before Simple, I used Celery. We use Celery at Simple. All of the ETL jobs that we have, or most of them that aren't streaming, are batch jobs. So we didn't really need Airflow. Airflow was out at that point and we said, we don't have any DAGs. Like we don't need a graph of jobs. They're just like scheduled batch jobs. We really need something that looks a lot like cron, but lets you write your jobs in Python because we had analysts writing jobs. So Celery was great, and Celery continues to work well for us. So, okay, this is PyData. I'm gonna talk a little bit more about Python because confession, most of Simple runs on the JVM. A lot of our services are written in Scala, Java, and Clojure, and that's because the company, one of the co-founders of Simple, was an early Twitter engineer and like authored a Scala book, right? But a lot of our engineers use Python every day for data science, analysis, ETL, connecting databases. I think every single JVM service I've written has a Python script in the root to do something, whether it's like load testing or like smoke testing or something like that. I end up using Python for all of my scripting work. And the other thing is you can build our entire pipeline with Python. Running JVM services like Zookeeper and Kafka doesn't mean that you need to interact with them with JVM languages, right? So there are some really good libraries out there written in Python to interact with these JVM tools. So you don't need to be writing Java. You can write Python, and there are some companies, a company called Parsley, that does this. They're streaming billions of messages through Python services with Python libraries. like these. So there's a really good Zookeeper library called Kazoo. We use Pika and Python Kafka to talk to RabbitMQ and Kafka within our Celery task worker. There's a really good blog post that benchmarks the Kafka clients, and they're really good. You can get huge volume through the Python clients. And then the last thing, Elasticsearch. So we have this search service. I think Elasticsearch and dynamic languages are really perfect for one another. This is an example of what it's like to write a query in Elasticsearch in Java. Basically, it's one big string, and then you have like a string builder and multiple builders, and you basically have to do string manipulation to build queries. That's so painful. Whereas in a language like Python, Elasticsearch takes JSON, so it's just a dictionary, right? You can basically compose and combine dictionaries that represent concrete ideas about queries together using Python to build your queries. So I think when working with Elasticsearch, like dynamic languages are the way to go when working with it. And that's it. That's all I've got. Do you have any questions? Yep.
Do you have systems for setting up all this infrastructure?
Yeah, we do. So the infrastructure team, they asked if we have systems for setting up the infrastructure. Yeah, so we work with Amazon's CloudFormation, and we have some sort of helper libraries to work with CloudFormation and build templates to set up our systems. So we have CloudFormation and Jenkins running. The data, I'm very lucky. I don't have to build those systems. We have an infrastructure team that like sets up the deployment. Like their job is to make it easier for us to stand up new services. So for us, it's go change the CloudFormation template, let them know that we're building this thing, that sort of thing. So. Yep.
Do you hire experienced data engineers? So that's a lot of stuff. Like, do you hire entry-level people? And if so, like, what do they look like? What is a typical hire that works in the staff?
The question was, do we hire entry-level data engineers? I think Simple's engineering staff is pretty top-heavy, to be honest. We have very few junior engineers, and I hope that changes. I think we need to hire more. I came into Simple never having written a single line of code that runs in the JVM, right? So I knew Python pretty well, I knew JavaScript pretty well, but I had to learn Scala and that sort of thing. And I think there, to be honest, there used to be more flexibility for that. I think we're actually going to focus more on junior developers, coming soon. As we get bigger, I think as an organization gets big enough, like you can't keep hiring senior developers the whole time. Like I feel like you sort of owe it to like the community to hire juniors and sort of build them up into seniors. So the answer is, I hope we get better at it. Yep.
I'm just curious to learn a little bit more about how you segment. So that's one of the components.
Oh, yeah.
And also just kind of anecdotal volume.
Yep.
Volume.
So the question was, how do we use segment.com? I have a very complex relationship with segment.com. We use them. The thing is that marketing and business folks often want to use various analytics providers and ad serving providers and that sort of thing. So we have basically our clients pipe all of their the client interactions all go through Segment first, and then come through Segment's webhooks to us for us to put in Redshift. And then once they're in Segment, the marketing people can send them to whatever third-party integration they want. All of our email integration goes through Segment first. So we send data to Segment, and then they send it to ExactTarget, our email provider. And sorry, what was your second question? Anecdotal data volumes. So what I say about Simple is Simple doesn't have big data. So we don't have a bunch of data where we don't have a huge data stream where we can afford to drop a little bit. We've got a small data stream where we can afford to drop nothing, right? Because we're a bank, you can't drop transactions. That's very bad. So I mean, to give you an example, like our search service, we're getting 10 or 15 messages a second, and other services. I think our highest volume service, like we're in the hundreds, right? We're not having to deal with thousands, tens of thousands, millions of messages a second. So it's a really nice problem to have. Like it's nice not having huge piles of data, but we sort of have different problems to solve because we can't really afford to drop any of it. So we have to have really resilient systems. All right. All right, thank you.